This is the start of Mazur's chapter 11, which is motion in a circle, and the file of slides will be phys8 slides 11.pdf. So when we think about moving in a circle, how should we best describe that? So a circle is the set of points in a plane whose distance from some origin O is a constant value r. So all of these points along the circle are a constant radius from the origin, and you know that if you draw a circle by taking a piece of string, you can trace out all the points where the string is the same length. Now what about moving in a circle? Maybe to describe moving in a circle, it's best if we watch one point move around. So as I spin this bicycle wheel, focus on the point that's marked with a piece of orange tape. So when we watched one spot go around on the circle, it would go around and around and around like this. So one instant it's here, and then it's here, and then here, 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 here. So it seems we could indicate at some point in time where the spot is. It's always a distance r away from the origin, and we can call this angle with respect to the horizontal theta. One thing to notice, as we go around and around, the velocity vector is tangent to the circle. So over here it points up, over here it points up and to the left, up here it points to the left, over here it points down. Now, as we go around and around, our velocity vector is constantly changing. Even if we're going at constant speed, the direction of the velocity vector is changing so that it is always tangent to the circle in which we're moving. So let's ask ourselves, what would be the direction of the acceleration when we're down here at this spot on the circle? Well, an instant earlier, our velocity vector pointed this way, and an instant later, our velocity vector will point this way. So here's a copy of that first vector. Here's a copy of that second vector. What do we have to add to this earlier vector to get the later vector? It seems like what we have to add points toward the origin. If we take the velocity vector a moment ago, in order to turn it into the velocity vector that we will have a moment later, we need a change in velocity which points toward the origin. So the change in the velocity vector per unit time seems to point toward the origin. So we will make a more convincing proof of that in a moment, but you can think about it as you watch an object go around and around and around, and you can imagine how does the velocity vector change from instant to instant. As we go around in a circle, the velocity vector is always tangent to the circle. So as we go around the circle, the velocity vector is tangent to the circle. Over here, it points, let's say, north-northeast. Over here, let's say it points north-northwest. So to go from the earlier vector to the later vector, you have to add something that points west. Over here, just before we cross this point, the velocity vector points, let's say, south-southwest. And here, it's south-southeast. To go from this earlier one to the later one, we have to add something that points east. Down near the bottom, the velocity vector just before the bottom points, let's say, east-southeast, and here it's east-northeast. So to go from the before to the after, we need something that points toward the origin. So I claim that the acceleration points toward the origin, in that each time as we go around the circle, if we're going around a circle at constant speed, but our velocity vector is changing, then I claim that the change in the velocity vector per unit time points toward the center of the circle. As we watch one point go around and around the circle, let's say that our distance from the origin is r. So this is r, this is r. And then let's say that we measure angles with respect to the positive x-axis. And let's say that this angle is theta. And we want to try to figure out how the coordinates x, y of this point relate to this radius and the angle theta. So let's draw a right triangle with the hypotenuse being the the radius, and then we have the x-coordinate horizontally from the origin to a vertical line projected down from this point, and then we have y, a vertical line projected down from this point to the x-axis, and so this height is y, this horizontal distance is x. So we can see that x over r is adjacent for this angle theta over hypotenuse is cosine theta, and y over r, so for this angle theta, this is opposite over hypotenuse, which is sine theta. That gives us x equals r cosine theta, y equals r sine theta. Notice that this continues to work outside of the first quadrant, so even if theta is larger than 90 degrees, we can come over here, and it's still true that x equals r cosine theta, y equals r sine theta. So for this angle, cosine theta is negative and sine theta is positive. Or if we were to continue down to this quadrant, then sine theta and cosine theta would both be negative. Or if we're down here, then sine theta is negative and cosine theta is positive. So this formulation works all the way around the circle. So if we're moving around in a circle, the natural question to ask after we've talked about what circle we're moving in is how quickly are we moving around the circle? So the simplest case to consider is that this angle theta increases by some constant amount per unit time. So the angle theta increases by a constant delta theta in every unit of time delta t. We want the rate of change of theta with respect to time to be some constant. Now, do we measure this rate of change of theta with respect to time in degrees per second or revolutions per second, maybe revolutions per minute or radians per second? We will see in a minute that radians per second makes the math work out most cleanly. So to say moving how quickly, we want to know what is the rate at which this angle theta changes. And initially, let's suppose that d theta by dt, the rate of change of the angle theta, is constant. And we will measure the rate of change of the angle theta in radians per second. So we'll measure theta in radians, so we'll measure its rate of change in radians per second. So we're going to define a quantity omega equals d theta by dt. This is lowercase omega. It looks a little bit like a W. You might be accustomed to seeing an uppercase omega. This is instead a lowercase omega. For reasons I don't understand, all of the quantities related to circular motion seem to be represented with Greek letters. Maybe it's the perfection of the circle that inspires us to name things in a way that is a tribute to ancient Greece. One way or another, tradition seems to dictate that we use lowercase Greek letters for things related to circular motion. So lowercase omega is angular velocity. It is the rate of change of the angle theta. And this is somewhat analogous to our earlier statement that velocity in the x direction is the rate of change of the horizontal coordinate x. So we will have omega is the rate of change of the angular variable theta. So we call it angular velocity. So we will measure angular velocity in radians per second. I'll show you why in a moment. But I have a digression for you. So if you want to earn an extra credit point or two on the next video reading assignment, you can check Wikipedia or your other favorite source and learn something about the origins of degrees to measure angles. And it seems as if this is an old enough tradition that it's largely speculation, but it's sort of, you can tell me what you find. And radians as a measure of angle. And the use of radians as a measure of angle seems more recent, so it seems to have a better established history. But if you're curious, and if you want to earn an extra credit point or two, then look these things up and let me know what you find. If you do this, you should somehow summarize in your own words, not just a copy-paste. I can read the Wikipedia as well as you can. but I want your synthesis or your synopsis. So the reason why we want to use radians is that it turns out that only by using radians to measure the angle theta rather than using degrees or revolutions do we get the familiar calculus results that the derivative of sine theta with respect to theta is cosine theta, and the derivative of cosine theta with respect to theta is minus sine theta. So if you were to use revolutions instead of radians, then you would have an extra factor of 2 pi in front of these results. You'd have to stick a 2 pi here, and you'd have to stick a 2 pi here. And if you were using degrees instead of radians, you would have to stick a factor of pi over 180 here, and you would have to stick a factor of pi over 180 here. So by using radians to measure theta, we get these nice clean results without superfluous factors of 2 pi or superfluous factors of pi divided by 180. So using radians makes the calculus more tidy. The way we define a radian is that when this angle theta equals 1 radian, then the arc length, which is the length measured along the circular path or along the circular arc from here up to here, equals the radius. So the angle such that this distance equals this distance is 1 radian, which is 360 degrees divided by 2 pi, which is 180 degrees divided by pi, which is pretty close to 57.3 degrees. And one way to see that is if you go all the way around the circle, then you go 2 pi r. So if you go a fraction 1 over 2 pi, which is about 1/6 of the way around the circle, then the arc length is r instead of being 2 pi r. So if you go 1/2 pieth of the way around the circle, then you bite off just 1/2 pieth of the circumference, so that is about 1/6 of the way around, so it's a little less than 60 degrees, 360 degrees divided by 2 pi, or 57.3 degrees. So when we measure angles in radians, if we measure the angle theta up from the x-axis in radians, then if this radius is r, then this arc length is r theta. So the arc length is the radius times the angle theta. And as a check, if we make theta be 2 pi so that we go all the way around, then the arc length is 2 pi r, which is the circumference of the entire circle. So the key of measuring angles in radians is that the arc length, how far you go around the perimeter of the circle, is just the radius of the circle times that angle in radian. So let's suppose that at time 0, we start out at theta equals 0, and let's suppose that our angular velocity omega is a constant. Then we would have theta equals omega t, since theta is 0 and t is 0, and the rate of change of theta is a constant equal to omega. So then here we would have theta equals omega t. So then we have x equals r cosine theta, which is r cosine omega t, and y equals r sine theta, which is r sine omega t. Then the x component of velocity is dx by dt, which is minus omega r sine omega t, which, by the way, would equal minus omega times y. And the y component of velocity is dy by dt, which is plus omega r cosine omega t, which, by the way, equals plus omega times x. And so you can see, so we had x is r cosine omega t. R is just a constant. The derivative of cosine theta is minus sine theta, and then you take the derivative of the inside, which is just omega. And then here we had r sine omega t r is just a constant. The derivative of sine is cosine, and then you take the derivative of the inside with respect to t, which is omega. You don't have to know how to do this. I'm just showing you where some of the results we're going to use come from. If you like, you can just use the results and not remember where they come from. Then we can work out the acceleration, which is the rate of change of velocity. So the acceleration, the x component, is the rate of change of the x component of velocity with respect to time. So the derivative of, this is a constant, this is a constant. The derivative of sine is cosine. So we have and we bring out a factor, derivative of the inside is another factor of omega. It's minus omega squared r cosine omega t, which is minus omega squared times x. And then the acceleration in the y direction is the rate of change of the velocity in the y direction with respect to time. So this is cosine omega t. Derivative of cosine is the negative of the sine. So we have minus sine. This is a constant, this is a constant. And then the derivative of the inside here is just a factor of omega. So this gives us minus omega squared r sine of omega t, which turns out to be minus omega squared times y. So one thing we can work out right away is the magnitude of the velocity vector. That should just be the square root of vx squared plus vy squared. And that is, so then vx is minus omega times y. We'll take that whole thing squared. And vy is plus omega times x. We'll take that whole thing squared, and then we'll take the square root. So this is, inside the square root, we have omega squared y squared plus omega squared x squared, and then there's a square root of all that. So this is omega times the square root of x squared plus y squared, and that is omega r, since the square root of x squared plus y squared is just the radius. There's another way to see that same thing. So we can say that the magnitude of the velocity vector is the square root of vx squared plus vy squared. And we can see that there's a factor of omega r in each one. So that's omega r times the square root of, so here we have sine squared omega t, and then here we have cosine of omega t. We're going to square that. So sine squared plus cosine squared of the same angle equals 1. So this is omega r times the square root of 1, which is just omega r. So this tells us that the magnitude of the velocity, which is just the speed, is omega times r. So the speed is the angular velocity times the radius. There is even a third way we can see that. If we call this arc length s, I don't know why it's called s in math, it seems to be a convention. So if we have the arc length s, then the speed is the rate of change of the arc length if we're really just moving in a circle. And this, we said that this arc length is r times theta. So the rate of change with respect to time of this arc length is the rate of change with respect to time of r times theta. And r is a constant, so that is r times the rate of change of theta. And we said that the rate of change of theta is omega, assuming we're going around and around in a circle at constant angular velocity. So this is r times omega. So this is one way we got that the speed, the speed at which we're going around in a circle, in other words, the number of meters per second is, well, I said r omega. Let's write it as omega r because that's the more conventional way to write it. So the number of meters per second is omega, which is the number of radians per second, times r, which is the radius. So meters per second going around the circle is radians per second going around an angle times the radius of the circle. Then, by analogous methods, the magnitude of the acceleration vector is ax squared plus ay squared, the square root of, which is, so ax squared, we could do it either this way or this way. Let's do it this way. So this is omega squared times the square root of x squared plus y squared. And the square root of x squared plus y squared is just the radius. So this is omega squared r. We could have also said, okay, let's do it. So we could have also said the magnitude of the acceleration is, you see we have this factor of omega squared r. So here's omega squared r times the square root of cosine squared omega t plus sine squared omega t. And you may remember that cosine squared of some angle plus sine squared of that same angle is 1. So this is omega squared r times the square root of 1, which is just omega squared r. So we have, when we're moving in a circle at constant angular velocity, then the acceleration has magnitude omega squared r. There's a more familiar way to write that. So we said that a is omega squared r, but we can take this result and let's solve it for omega. We get omega is v over r if we're moving in a circle. So then we get the acceleration is v over r, square that, times r. So then you get two factors of v, but only one factor of r, because this cancels, and this is v squared over r. So the magnitude of the acceleration when you're moving around and around in a circle at constant angular velocity and constant radius, since it's a circle, is v squared over r. So when moving in a circle at constant angular velocity omega, in other words at constant speed, v equals omega r. So if we're moving in a circle, then we're moving at constant radius r. And if we're moving it around and around at a constant angular velocity, then we have a constant speed. V is omega times r. In other words, meters per second is radians per second times the radius. So if we're doing this, we're moving in circular motion at constant speed, which is the same thing as moving in circular motion at constant angular velocity, then the acceleration has magnitude v squared over r, which may be familiar to you. That also equals omega squared r, which may be less familiar to you. And we will confirm in a minute what we argued earlier, that this acceleration, when we're moving in a circle at constant speed, points toward the center of the circle. And we'll also see in a minute from here that the velocity vector points tangentially. So when we're moving in so-called uniform circular motion, we're going around and around in a circle at constant angular velocity. And by definition of a circle at constant radius, the acceleration will point toward the center of the circle and will have magnitude v squared over r, which is the same as magnitude omega squared r, and the velocity vector will point along a tangent to the circle and will have magnitude omega times r. This is a little bit too mathy, but while we're here, while we have all this stuff here, I want to try to argue that the acceleration does in fact point toward the center of the circle. This is when we're moving in circular motion at constant angular velocity, and that the velocity vector does point along a tangent to the circle using all this math that we just worked through, even though you can just tune out the math if you don't like math, but if you do like math, you might find this illuminating. So remember, back in chapter 2, we introduced the r vector, and the r vector seemed kind of pointless. We didn't quite understand it. Well, now it's actually a little bit convenient, so we can say that the r vector collects x and y together in a dotted pair, in an ordered pair. The r vector collects x and y together in an ordered pair. So the x component of the r vector is big R cosine omega t, and the y component of the r vector is big R sine omega t. And then we worked out a moment ago that the velocity vector, whose components are velocity in the x direction and velocity in the y direction, the x component of velocity is minus omega times y, and the y component of velocity is plus omega times x. We worked that out using the cosine and sine stuff. And then, if this is true as long as we're moving in a circle centered at the origin, and then if omega is constant, so if we're at constant angular velocity, then the acceleration vector, whose components are a sub x and a sub y, the acceleration in the x direction and the acceleration in the y direction, it has an x component, which is minus omega squared times x, and it has a y component, which is minus omega squared times y. So it actually points in the negative r direction. So you can actually see, since omega squared must be positive, so this vector points, if the r vector points from the origin out toward the point where the object is, then the acceleration vector points back toward the origin. You can see, because this is proportional to minus r, this vector points toward the origin. So you can see already that the acceleration points toward the origin if you like vectors. The magnitude of this acceleration vector is omega squared times big R, the radius of a circle, and using this result we can say that that equals v squared over r. And again, this is true if we're moving in a circle at constant angular velocity. So here's an example. So suppose we say that we are at 45 degrees, but we're supposed to be radians, so that's pi over 4. So let's suppose theta is pi over 4, which is the same thing as 45 degrees. And then let's make the radius be square root of 2 meters. And that's convenient because then we have 1 meter this way and 1 meter this way, giving us root 2 meters this way. And then just to make the math easy, let's make omega be 1 radian per second. Now, one thing I didn't tell you yet is because radians are dimensionless, in other words, the radian is really just kind of a ratio of distance on the arc to distance along the radius. So even though radians are radians, radians basically have no unit. So a radian per second is the same thing as a per second. That's a little bit tricky. So when you multiply by omega, you think you're multiplying by something in radians per second, but you drop the radians and you say it's just you're multiplying by per second. We'll see that in a minute. So then the radius vector, which points from the origin to this point xy, it's plus 1 comma plus 1 meter. Well, that makes sense. To get from the origin to this point, it's plus 1 comma plus 1. You see, we move plus 1 in x, and we move plus 1 in y, and that brings us over to plus 1 comma plus 1. Then the velocity vector is omega times minus 1 comma plus 1, because it turns out we just swap the x and the y and we negate the y. Well, swap the x and the y and negate the first one. So that is minus 1 comma plus 1 meters per second. You see, we turned radians, we multiplied meters by radians per second, and we got meters per second because the radians really have no unit. So this is minus 1 meter per second in the x direction and plus 1 meter per second in the y direction. What does that look like if we draw it? Well, you see 1 comma 1 goes this way, minus 1 comma plus 1 goes this way. Because you see, so plus 1 would go like northeast. You see, minus 1 plus 1 would go northwest. So that makes sense. And then another kind of cool thing you might see here if you like vectors is if you take the dot product of this velocity vector with this position vector, then you'll notice that the dot product equals 0. So in other words, r dot v equals 0. That means that this velocity vector is perpendicular to this radius vector. Yeah, this vector is perpendicular to this vector. That's just another way of saying that this points along the tangent line because it's perpendicular. So you take the line from the origin to the object, and the tangent line is perpendicular to that. So that's kind of neat also, which is a true statement if you're moving in a circle. Then one more thing is that for these numbers, the acceleration is minus omega squared times x comma y. Well, we had x is 1 meter, y is 1 meter. So this is minus 1 meter per second squared, comma, minus 1 meter per second squared. So that tells you that the acceleration vector points this way because it points in the minus 1 direction in x and the minus 1 direction in y. So that's diagonally in toward the origin. So that also makes sense because we said that the acceleration should be toward the center. So we see in this example that works out to be true. And it's also true that this acceleration vector is perpendicular to this velocity vector, that's true if you're moving in the circle at constant speed. Right, so we can also work out, if we wanted to, that this acceleration vector is perpendicular to the velocity vector, and if two vectors are perpendicular, then their dot product is 0. So we can work out that the acceleration vector dot product, the velocity vector, is 0. How would we do that? Well, in this case, we said that the acceleration vector is minus omega squared times x comma y. Oh, that's just a multiply. And then the dot product with omega minus y comma plus x. And I guess I won't write out every step, but you see, if you multiply this out, you get x times minus y, and then you would add that to y times x. So x times minus y would just cancel the y times x. So you would get 0 for this dot product. And there's a similar thing that happens when you take the dot product of this position vector with the velocity vector. You get x times y dot product with minus y plus x. So the x times minus y would just cancel out with the y times plus x. Finally, after all that math, we are on slide 1 of Phys 8 slides 11.pdf. So this is motion in a circle. So if you go around in a circle at constant speed, your velocity vector is always changing direction. So this is, because of gravity, this is not exactly constant speed. This would be constant speed, but it's harder for you to see. So let's just pretend that this is close enough to constant speed. So even if I am going around at constant speed here, my velocity vector is always changing direction. Therefore, I must be accelerating. So a change in velocity, whether it is a change in magnitude or a change in direction or both, requires acceleration. Not just requires acceleration, it is acceleration. So a change in velocity, well, with respect to time, is acceleration. So if you're moving in a circle of radius r at constant speed v, then the acceleration is v squared over r, and that acceleration points toward the center of the circle. It's called an centripetal acceleration. So this is called centripetal acceleration, and it points toward the center of the circle. In the absence of a force, so in other words, if the vector sum of forces is 0, or if there are no forces, then there is no acceleration and therefore no change in velocity. So you know that if in the absence of a force, or in the absence of an unbalanced force, an object will continue at constant velocity. That constant might be 0. So an object will continue at 0 or constant velocity. So for motion in a circle of radius r at angular velocity omega, and we've defined omega to be the rate of change of the angle theta. So omega is d theta by dt, right? Theta is the angle of our circular motion going around, and omega is the time rate of change of that angle. And we're measuring angles in radians. So then the speed, if you're moving in a circle of radius r at angular velocity omega, then your speed is omega times r. So this is meters per second equals radians per second times the radius in meters. And the velocity vector v is tangent to the circle. So you're going around in a circle, and the velocity vector is tangent to the circle. That's not quite tangent. The velocity vector is tangent to the circle. Okay. Then, if omega is constant, so if we're going around and around the circle at a constant number of radians per second, which is equivalent to a constant number of revolutions per second, which for constant radius is equivalent to constant speed. So if omega is constant, then the acceleration points toward the center and has a magnitude v squared over r. So the acceleration points toward the center of the circle, and it has magnitude v squared over r, which might be a familiar expression, and that is identical to omega squared r, because you can just plug in v equals omega r, and you can see these two expressions are the same. Omega squared times r, or v squared over r. And there are different times when one or the other will be more convenient. So this is called the centripetal acceleration. So the centripetal acceleration equals v squared over r, where r is the radius of curvature of the path that you're bending in. So in order to bend an object which is moving at speed v into a circular path of radius r requires a centripetal force. That means a force directed toward the center of the circle, whose magnitude is mv squared over r, and it points toward the center of the circle. So you are looking down. Imagine a plan view. You're looking down as I spin an orange ball on a string above my head in a circle at constant speed. The string breaks at the instant shown below. Which picture depicts the subsequent motion of the ball just the instant after the string breaks? Now what you have to imagine is that the force, the centripetal force, which is causing the ball to move in a circle, is the tension in the string. And if the string breaks, then that tension in the string disappears and we no longer have a centripetal force directing the object to move in a circle. So if the centripetal force disappears, then the object will subsequently go at constant velocity. So what is its velocity vector the instant that the string breaks? And is there any force that would cause it no longer to take that same path, to go at that same velocity? I guess, well, we're looking at a plan view, so either we can pretend that gravity doesn't exist, or we can acknowledge that if gravity had an effect, it would be invisible to the plan view because it would be basically into the plane of the paper. So let's just pretend there is no gravity, since if it were there, it would cause motion, it would cause acceleration into the plane of the paper, which we can't see on a plan view. So then what is the subsequent motion of the ball? I think that once the string breaks, the ball's velocity will just continue to be what the velocity of the ball was the instant the string broke. Which picture is that? So in this picture A, the ball would shoot radially outwards. I don't think that makes sense because I think the ball's velocity the instant before the string broke was this way. It was tangential to the circle. And so I think C and D also don't make sense because, again, the circle is this way. So the ball's velocity the instant before the string broke was this way. So the ball's velocity the instant after the string breaks will be that same velocity because there's no longer a force pointing toward the center to deflect the ball toward the center. So I think I like B, bravo, because the velocity vector immediately after the string breaks should be the same as the velocity vector the instant that the string breaks. And it should continue with that velocity unless there's some other force that we don't know about. But I mean, so then assuming that there are no other forces acting in the plane of the picture, and I don't see why there should be, because the only other force that comes to mind is gravity, which would be perpendicular to the plane of the paper, then I think the ball will then just continue on this path like that at constant velocity. So now I'm going to show you a demonstration where we have a turntable, and tied to the edge of the turntable is a piece of string, and dangling from that piece of string is a nut. And if you say the nut has mass m, and the turntable is just sitting idle, not turning, then what is the tension in the string? I think it should equal the weight of the string, mg. The next question is, what will happen when I start the turntable spinning? What do you think is going to happen when I start the turntable spinning? Maybe the nut will just continue to hang down vertically. Maybe the nut will be deflected inward, or maybe the nut will be deflected outward. And if it is deflected, how will that deflection depend on at what speed the turntable turns? Well, we could say that when I start the turntable spinning, the nut will continue to hang down vertically, or maybe the nut will move inward somewhat, making some angle phi with respect to the vertical axis, or maybe the nut will move outward somewhat, making some angle phi with respect to the vertical axis, so then maybe it would look like here's an angle phi, and maybe it will instead kind of dangle out this way. Which of those seems more plausible to you? I guess we can just try the demonstration and see. So I've started the turntable spinning, and I think you can see the string is now deflected a little bit outward. So I think what happened is that the nut deflected outward, as we saw in the demo. So now what will happen if I spin the turntable faster? So let's let T be the tension in the string. So which of these options seems to make sense? A, the nut will move farther outward if I spin the turntable faster. Tension times the sine of this angle phi provides the centripetal force mv over r squared, while tension times cosine phi balances gravity mg. Well, let's see, is it mv over r squared or is it mv squared over r? I guess that's one thing that distinguishes the answers from each other. And then also, which one is providing the centripetal force? Is it t cosine phi or is it t sine phi? So maybe we should draw a free body diagram for the nut. And what are we going to put on our free body diagram for the nut? I guess there's a gravitational force by Earth on the nut, whose magnitude is mg. And then it seems like the only other force acting on the nut is the tension, but we know the tension is directed at some angle phi with respect to the vertical. So let's call this here's the magnitude t, which is the contact force by the string on the nut. And then this angle with respect to vertical is phi. There are a couple different ways you can draw phi. You can write the Greek letter phi like, that's not very good. You can write it like that, or you can write it like that. So I write it usually either like this or like this. Let's be more straightforward. Now, a question we have to ask is the nut accelerating? And I think it is accelerating. It's accelerating toward the center of the turntable. So in fact, I think the centripetal acceleration is v squared over r. Then I think we want to decompose this tension force. So let's decompose the tension force into this component and this component. So we'll cross this out. And this is a little bit tricky, but if we take phi, then you see adjacent over hypotenuse. Adjacent over hypotenuse is this vertical component. So this is actually t cosine phi. And then we have opposite over hypotenuse is this horizontal force divided by the original force. So this is actually t sine phi. So then we can write Newton's second law, F equals ma, in two different dimensions. So in the vertical, so we have the acceleration is purely horizontal. So vertically we have 0 acceleration equals up minus down, t cosine phi minus mg. And then horizontally, the acceleration is to the left. So I could use x component to make the x component be negative, but there's only one force here. So let's just write it this way. So we'll say mv squared over r equals t sine phi. Now you see, I guess to follow my convention, I would have said that the x-axis points to the right, and then this would be an acceleration in the minus x direction, a force in the minus x direction. Or I could have said the x direction points to the left. But in any case, the acceleration is this way, and the force t sine phi is this way. So mv squared over r equals t sine phi. So then what does that imply about the angle phi? I think we can say that the tangent of this angle phi with respect to the vertical is v squared over gr, because we can take sine phi divided by cosine phi, and that gives us this expression divided by this expression. If we go back to the multiple choice question, the centripetal force is mv squared over r, so it must be either c or d. And it turns out that t sine phi provides the centripetal force, while t cosine phi balances gravity. And that sine and cosine are backward a little bit from what you're accustomed to, because in this case we're measuring phi with respect to the vertical, whereas more commonly we measure theta with respect to the horizontal. Then the same free body diagram that I drew on the board here appears on the slide, and we can see the conclusion that I reached, which is that the tangent of this angle is v squared over gr. So we can write F equals ma both vertically, where the acceleration is 0, and horizontally, where the acceleration is v squared over r. Increase the rate of rotation of the turntable. Let's see what it looks like. Did you correctly predict that as I increased the rotation rate, the string would achieve a larger angle with respect to the vertical? So that seems to continue to be true if I make the rotation rate even a little bit faster. So now, suppose friction provides the centripetal force instead of a component of the tension of a string. So suppose a highway off-ramp that I often use bends with a radius, a bending radius of 20 meters. So it's like an arc of a circle whose radius is 20 meters, and it's entirely in the horizontal plane, right? So there's no banking of the road, it's just a flat road. I notice that my car tires allow me in good weather to take this off-ramp at 15 meters per second without slipping. So I think what that must mean is that if I go at 15 meters per second, then the maximum possible force of static friction exactly provides the necessary centripetal force. So how large does the off-ramp's bending radius need to be in order for me to take the same turn at 30 meters per second? Well, it's not the same turn. I mean, same tires, same pavement, but suppose we can rebuild the road so that instead of being safe at 15 meters per second, it is instead safe at 30 meters per second. So how would we scale it? Well, let's think. I think we can argue that the maximum possible static friction equals the required centripetal force. So then mu static mg, since F normal just equals mg, since it's a flat level road, would equal mv squared over r. And we want to know what the bending radius is at this maximum. Well, it seems like the mass cancels out. So arguing that the maximum possible static friction, which is where F static equals mu static times the normal force, and the normal force is just mg for a flat road, then so if that static friction equals the required centripetal force, we get mu static mg equals mv squared over r, where r is the bending radius of the road. We can just solve for r, since we want to know what's the minimum bending radius to be able to get around the road without slipping. So it's the speed squared divided by mu g. So the speed squared divided by the friction coefficient divided by little g. So then we could just write, okay, what's the radius of the new required radius to the old required radius? So we write this expression up here for the new situation, this expression down here for the old situation. Everything just cancels out except for the ratio of the square of the speeds. So it's really just the new speed divided by the old speed, that quantity squared. So if I want to go at twice as big a speed, so v new over v old is 2, then we must have r new over r old is 2 squared is 4. So I guess we have to take the road radius and go from 20 meters to 4 times 20 meters, which is, I think it's 80 meters. I think that makes sense because the expression v squared over r is the same. If you multiply v by 2 and you multiply r by 4, then this expression v squared over r is unchanged. And that makes sense because the available static friction is unchanged, because this is just the weight of my car times mu static. Now here's a demonstration where I'm going to put several coins onto a turntable, and the turntable is going to go around and around and around, and they're all identical coins, and they're all on the same type of surface. And the question is, as I spin the table faster and faster and faster, will all the pennies fall off at the same time? Or will the inner pennies slide off first? Or will the outer pennies slide off first? Or is it impossible to predict? So when you think about these pennies going around and around and around, you might want to ask, what do they have in common? They're all on the same turntable. Like an old record player, you set the record player for revolutions per minute. So does this penny have the same speed as this one, as this one, as this one? Or does it have the same angular velocity? So is it the meters per second that are the same for all the pennies? Or is it the radians per second that are the same for all the pennies? And I think, what do you think? I think it's the radians per second that are the same for all the pennies, because they, every penny makes a revolution of the table the same interval as every other penny makes a revolution of the table. So I think they all have the same value of omega, but they might have different values of speed because they're at different radii. Let's adapt the setup with the turntable and the nut from a moment ago, and instead we have placed a bunch of pennies, copper pennies, on the surface of the turntable, and right now everything is just sitting stationary. But what do you suppose will happen if we start the turntable rotating? Let's initially start the turntable rotating quite slowly. I think we sort of answered this already, but I put several pennies on the turntable at several different radii, and I turn the turntable slowly enough that all the pennies stay put. Which of the following statements is true? Do they all have the same velocity? Do they all make the same number of revolutions per second? Well, I think I like that. I don't think they all have the same velocity, because you imagine this one has to go around a much bigger circle in the same time as this one goes around a smaller circle. All pennies have the same angular velocity, omega. Omega equals v over r. But r will vary from penny to penny, so v will also vary. I think I like that. Oh, so I think B and C are both true. Yeah, so I think I like answer D here. In this case, how can I best express the centripetal acceleration for each penny on the turntable? Well, I could say A is v squared over r. That's a true statement. Well, I could also say A is v squared over r, and since v is omega r, then that's r times omega squared divided by r, which is omega squared r. I think A and B are both true statements. B is starting to look more useful. Acceleration is the same for all of the pennies on the turntable. Well, that is false, because I think they're at different radii, but they have the same omega. Okay, A and B are both true, but B is more useful in this case because the speed varies from penny to penny, while the angular velocity omega is the same for all pennies. Oh, I think I like D. So I guess, A, B, and no, I don't like any of those. Okay, no, so I don't like those. Well, no, I don't like those. All right, I think I like D, delta. So it is true that we have mv squared over r for the centripetal force needed to keep the pennies on the turntable, but that's not very useful because the different pennies have different speeds. But m omega squared r is a more useful expression because they all have the same omega. So now you can think, well, is it the pennies at little r or the pennies at big R that require a bigger centripetal force to keep them on the table? And what is the maximum size of that centripetal force if it's static friction? So now we know that the centripetal acceleration can be written A centripetal equals omega squared r, and it varies with the radius of each penny. And we also know that static friction must provide the force m omega squared r to keep each penny going in a circle. Can we predict which pennies will slide off of the turntable first as I gradually increase the angular velocity of the turntable? Will the inside pennies fly off first? Well, that makes sense because for a given speed v, your tires screech more when you go around a turn with small radius than when you go around a turn with large radius. The outside pennies will fly off first. This makes sense because omega is the same for all pennies. V is not the same for all pennies. M omega squared r is largest for the outermost pennies. Oh, I think this sounds pretty good. Or they all slide off at the same time, or there's no way to predict. Well, I think, you see, when a given penny slips, it's going to have mu static mg, that's the maximum possible static force, equals m omega squared r, which is the centripetal force that static friction needs to provide to keep the penny going in a circle. So I think this maximum will be reached sooner for big R, because you can reach this maximum at a relatively small omega if r is big, and then as r gets smaller you need a bigger omega to reach that same maximum. So I think that as we gradually increase omega, we're going to see the pennies at big R slip first, because the pennies at big R will be the first to reach this maximum value of friction, and then friction will let go. Let's see what happens in the real demonstration. Okay, so let's go. Do we expect all the pennies to slide off at the same time? And if not, which ones should slide off first? The ones on the inside or the ones on the outside? As we gradually increase the rate of rotation. Here's a kind of digression. So imagine it's kind of like a fish tank, but it's actually more like a slice of a fish tank. Like if you took a fish tank and you made it really narrow, kind of like this board. And so now you take this fish tank and it's filled with water, and the water has a coloring to make it easy to see. And now you have a axis of rotation going through the middle of this tank of water. So this is, gravity points down here, but now I start the thing spinning on a turntable. And then the question is, well, will the rotation affect the shape of the water surface? And you want to think like centrifuge. What happens in a centrifuge? So you could say, well, maybe the water doesn't care. It'll just mind its own business. Or you could say, well, maybe all of the water will instantly go to the very edges of the tank immediately. Or maybe something in between will happen, and maybe you'll get kind of a curved shape. And if you do get kind of a curved shape, well, how do you know what kind of a curved shape you'll get? So I would say use as a hint. Do you remember when we had the nut on the turntable? When we had the nut on the turntable, we had the tangent of this angle with respect to the vertical was v squared over gr. So this will be tricky to follow, but I claim that, actually all the water is going around not at the same speed, but at the same omega. So we want to change this v squared over gr to omega squared r over g, using the same trick that v equals omega r. And then when you watch the water in this pail, r is actually how far out it is from the center, and then let's say y is the height of the water. So I claim, you kind of have to just take this on intuition, but I claim that the surface of the water will do something very analogous to what the nut on the end of the string did. And I claim that we'll see the tangent of the angle of the water surface with respect to the horizontal in this case should go like this ratio omega squared r over g. And if x is how far out we are, it's omega squared x over g. Also, this tangent of this angle is basically dy by dx. So it's like rise over run as the tangent of this angle. So I claim that we have dy by dx is omega squared over g x, and then that gives me y is proportional to x squared, which is a parabola. So I claim, and you don't have to follow any of this, it's just for fun, but I claim that we're going to see a parabola, that the height of the water will be proportional to the square of how far out we are from the axis. Basically for this reason, so that the angle with respect to the horizontal will be proportional to how far out we are. And that is basically the equation for a parabola, because it says that the slope is proportional to how far out you are, and that's true for a parabola. We actually have a live demonstration version of this, but it's currently broken. So instead, you can look at this video version.
Here is a turntable with a fluid accelerometer sitting on it. The fluid is water, made green with food coloring. The water is in a thin tank, a narrow wall of liquid, so we can easily see what happens to the water as it spins. What shape is that? And why does the water surface take that shape? See if you can figure it out. You can also watch my follow-up videos for both conceptual and mathematical explanations.
And you do see, in fact, a parabolic shape of the water surface. How does a salad spinner work? Maybe the outer wall of the salad spinner provides the centripetal force that pushes the lettuce toward the center of rotation, but the water feels no such force because the water can sneak through the holes in the outer wall, thus separating the water from the lettuce. That actually seems pretty good, right? Because you have this kind of screen-like surface, and so it pushes inward against the lettuce, so the lettuce does feel a centripetal force toward the center, which keeps it going in a circle, whereas the water does not feel that centripetal force because it can flow through the screen-like outer surface of the salad spinner. So that seems pretty good. I really want to say centrifugal force, even though my high school teachers told me there is really no such thing as centrifugal force. It's just a pseudo force that one perceives when observing from the confusing perspective of a non-inertial reference frame. This is a profound statement. which is a little bit outside the scope of this course, but I have been tempted for a long time to talk about it. So if you observe things from the perspective of an accelerating reference frame, and you see, if you're observing things from the perspective of sitting at this little spot on the outer edge of the salad spinner, then you are accelerating this way. So if you imagine, just think for a minute about you're riding in a car. Here you are. You're riding in a car, and suppose the car is accelerating this way. Well, if the car is accelerating this way, now imagine your coffee cup. So here's your coffee cup sitting on the dashboard of the car. So if the car is accelerating forward, then from the perspective of this non-inertial reference frame of the car, when the car accelerates forward, you think the coffee cup experiences a backward fictitious force. It's really not true. If you look at it from the point of view of the sidewalk, the car is accelerating forward and the coffee cup is just continuing at constant velocity, or part of it is. So it appears to the inside occupants of the car as if the coffee cup accelerates backward, but really it's just that the coffee cup fails to accelerate forward along with the rest of the car. So then the coffee spills onto your lap. So this is completely outside this course, but if I am in a reference frame, if I have an object M, object of mass M, observed from a reference frame, and that reference frame is accelerating with acceleration A, then there's this fictitious force, which is called the inertial pseudo-force, fictitious force, which is minus ma. So in other words, if I am the coffee cup sitting here in the car, and the car is accelerating forward with an acceleration a, then if you want to analyze what you think you see happening from the perspective of the inside of the car, it actually looks to you as if the coffee cup experiences a force ma, where a points opposite the acceleration of the car. This is a total digression. So you see, if you look at it from the perspective of this little blob inside the salad spinner, you know that this little piece of salad spinner is experiencing it's experiencing an acceleration. It is accelerating toward the center with magnitude v squared over r, or you could say omega squared r if you like. And so if you were looking at it from the point of view of like a camera mounted on the inside of the salad spinner, and if there's a little water droplet, suppose there's a little water droplet of mass m here. This is a digression, but it might be a fun digression. There's a little water droplet of mass m here. Then what you will think you see is that the water droplet experiences a fictitious force, which is the mass of this little water droplet, and there's a minus sign, and there's the centripetal acceleration. So in other words, you think that the water drop is experiencing an outward acceleration when in fact it's just failing to spin around with the rest of the contents of the salad spinner. So that's the kind of centrifugal pseudo-force explanation. But let's back up a little bit and not go there. So that also explains, that same explanation will tell you, like, you can interpret why the books fall off of your bookcases during an earthquake and so on. It's because the frame of the building is now accelerating. And so if the building is accelerating that way, then from your perspective, the books on your bookcase are experiencing a fictitious force this way. But really, if you just step outside the building and you observe, let's say you observe from like a drone hovering above the ground, then you'll see the story from the perspective of the inertial frame, and you'll see, aha, the building is accelerating that way, and the book is just not accelerating with the building, and that's why the book falls off the bookcase. Okay, that was a digression. Maybe it was a fun one. I hope it was fun. I guess you could say A or B, but A is the way we've learned to analyze the situation methodically from Earth's reference frame. We have not learned how to do calculations in non-inertial reference frames. That is true. There's actually a really cool video where you can see a dad with his kids driving in a car, and they accelerate forward and accelerate backward, and there's a helium balloon in the car. And you can see as they accelerate forward, the helium balloon actually leans forward. And as they accelerate backward, the helium balloon actually accelerates backward. And that's kind of interesting to ponder. And it's because normally the helium balloon points up, which is opposite gravity, but instead now the helium balloon will point opposite the vector sum of gravity and the kind of fictitious force caused by the car's acceleration as seen from the point of view of the inside of the car. I'm still digressing. While the obvious answer is A, I'm so fascinated by pseudo-forces that appear in non-inertial reference frames, I want to read the Wikipedia article on the Coriolis effect. You could do that, actually. If you do read the Wikipedia article on the Coriolis effect, and if you learn something worthwhile, you can let me know for an extra point. Anyway, I think what we will observe is that the salad experiences a centripetal acceleration which keeps the salad moving in a circle, whereas the water can slip out. And I think I actually been meaning to find a transparent salad spinner so I could make a video of this, but I think we will see that the water shoots out tangentially like this, because the water just continues moving in the direction it was already moving, which is tangential, whereas the salad gets accelerated toward the center so that it can move in a circle. But I'd really like to make a video to see if I can confirm this. Here, you can read this. I won't read it to you. Here's an example of a good answer to the salad spinner question. Suppose I try to spin a pail of water in a vertical circle at constant rotational speed with the water a distance r from the pivot point at my shoulder. So I guess that means I'm kind of spinning the water like this, although here, let's just do it like this so that you can... So now imagine instead of a tennis ball, this is a pail of water. And the question is, will the water fall out of the pail? So A, the water will fall out while the pail is upside down, no matter how fast you spin it around. B, the water will stay in the pail no matter how slowly you spin it around. I think B might be true if it were frozen in the form of ice. C, the water will stay in the pail as long as you spin it fast enough. Fast enough means v squared over r is bigger than g, or equivalently, omega squared divided by r is bigger than g when the bucket is upside down. Oh, let's think about that. The water will stay in the pail as long as you spin it fast enough. Fast enough means v squared over r bigger than g, or equivalently omega squared r bigger than g. Aha, when I read C, I knew there was something fishy. Right, so okay, I think we could rule out C because C just has a math error in it on purpose. So I think I like D, delta. And so we'll demonstrate that, but see, when you look at the tennis ball spinning on the string, what happens if I spin it too slowly? If I spin it fast enough, the string is always taut. Now watch what happens if I don't spin it quite fast enough. You see, the string goes slack at the top. So if I spin it too slowly, the string goes slack at the top. So that's because the string can pull on the tennis ball. The string cannot push on the tennis ball. With the water in the pail, we have a very similar situation. The bottom of the pail can push on the water, but unless the water is frozen, the bottom of the pail cannot pull on the water. So I think keeping the water in the bucket when it's upside down is exactly the same problem as keeping the string taut while the ball is in its vertical position. So let's watch the demonstration, and then let's do a free body diagram for the water at the instant when the bucket is upside down. I have quite a bit of water here. This seems like enough water that I could really get quite wet if something bad happens. Whoa, okay. So the water level seems to be up to about here. So we've kind of filled this bucket. I think we just argued that if I don't go fast enough, I'm going to get wet. So I have to try to go fast enough that I won't get wet. So let's see if I can go fast enough. Whoa, look at that. So it seems like I actually am going fast enough not to get wet. And actually the place where you really are in danger of getting wet is when you decide to stop, because somehow going from twirling around to not twirling around, there's that point in the motion where you're not going too fast. Let me try it again this way. Whoa, oh, we almost got wet. Okay, so like I wasn't quite going fast enough there. And let me see if I can also make it work with this kind of motion. Oh, okay. Yeah, so we can try that. Okay, we haven't gotten wet yet. That's pretty good. And here, let me just point out to you that there really is, oh, look at that. There really is water there. Let me try it with one other contraption. The last time I tried this contraption, the handle fell apart and parts went crashing all over the floor. So let's just see what happens. So this is a beaker. This is water that's been colored with some food coloring so that it's easier for you to see. So here we go. So the beaker is on top of this plate, and the plate has a kind of handle we can use to hold it. And you know, because this whole thing fell apart, not because the physics didn't work, but because it fell apart, I'm going to close my computer. And I think I'm going to cover up my computer. So the claim is that I should be able to keep this thing, not only does the water not fall out of the beaker, but I am told, and again, I'm not sure how much, I'm told that even the beaker will not slip off of this plate, because I thought in past years the beaker was glued down to the plate, but now I'm told that I don't even need to attach the beaker to the plate with any tape. I'm a little skeptical of that. I think that means I really have to make an effort to keep this going at a decent speed. Whoa, wow. You know, I did not actually think that I knew that the water would stay in as long as the beaker stayed in place, but I did not think that I would be able to keep the beaker from sliding on the plate. I guess I did. I thought that was pretty impressive. The way to think about the water in bucket problem is the bottom surface of the bucket can both push and pull on the water as if the water and bucket were glued together. I think that's only true if the water is frozen. The bottom surface of the bucket can push on the water, compressive force, but it cannot pull on the water, no tensile force. If the required centripetal acceleration is large enough that the bucket must push on the water to keep it moving in a circle when Earth's gravity, even when Earth's gravity is pulling down on the water, then the water will stay in the bucket. I think I like that. When the bucket is upside down, the bottom surface of the bucket must pull up on the water to keep it inside the bucket, or else the water will spill out. No. As a matter of fact, the bucket can't pull up on the water unless the water is frozen to the bucket. The water stays in the upside down bucket if the outward centrifugal pseudo force, magnitude mv squared over r, or m omega squared r, is at least as large as the downward force of gravity. Well, okay, this is a digression again. I think you could say B or D, but we haven't learned in this course how to analyze pseudo forces that one perceives when working in a non-inertial reference frame, so I prefer B, Bravo, which uses Earth's reference frame. I think I like E here, echo. So I like this explanation. This is the way you explain it from the perspective of looking from the room, from the classroom perspective. From the perspective of the water itself, you could say d delta, but we don't know how to do that in this course unless you really carefully followed my digression a few minutes ago. To analyze this, we want to consider the instant when the bucket is upside down. So the bucket is moving around and around and around in a circle, but consider the instant when the bucket is upside down, since that's the time when the water is most likely to fall out of the bucket. And I claim that the water will stay in the bucket if the bucket is pushing on the water. If the bucket, in order to keep going in a circle, if the bucket would have to pull on the water instead of push on the water, then the water will fall out. And I guess my analogy for that is, if you imagine my ball on a string, then I can keep the ball going around in a circle if I go fast enough. Notice, if I don't go fast enough, if I go a little bit too slowly, then you can see that the string becomes slack at the top. But now imagine that instead of spinning the ball around on a string, imagine if I spun the ball around at the end of a metal rod. That would be okay, right? I could go around as slowly as I like at the end of a metal rod, and it would still go around, because the metal rod can either push or pull on the ball. You don't see a metal rod here, but you have to imagine it. By contrast, a string can only pull, it can't push on the ball. So I think if we look at the moment when the bucket is upside down and we draw a free body diagram for the water at that moment, then the water is accelerating toward my hand. My hand is the center of rotation. So the water is accelerating toward, this is not an m, there's no m, it's v squared over r. So the acceleration is v squared over r toward my hand. And there's a gravitational force downward on the water by Earth. So this is Earth on water, is mass of the water times g. That's a downward force. And then there's a contact force by the bucket on the water. And I've drawn it pointing down. So if we get a negative number, that will mean it's pointing up. But you see, if you look at this, the bucket in this orientation is able to push down on the water, but the bucket is not able to pull up on the water again, unless the water is frozen to the surface of the bucket. And the acceleration is down and has magnitude v squared over r. So if we write Newton's second law along the y-axis, so I drew the y-axis pointing up here, then mass of the water times the acceleration of the water in the y direction. So that means, so if I make the y-axis point upward, then the acceleration of the water in the y direction, the y component of the water's acceleration at this instant is minus v squared over r, because the acceleration is downward. So if the y-axis points upward, then the y component, there is no x component of acceleration, and the y component is minus v squared over r. So then mass of the water times the acceleration of the water in the y direction is minus this force in the y direction minus this force. Well, it's the sum of the y components of these two forces. These are both in the minus y direction, so they're both negative. And then this acceleration is in the minus y direction. So this is minus mass of the water, v squared over r, is minus this contact force, minus mg. I guess I could have made them all plus. So then if you move the contact force by the bucket on the water over to the left, and then if you move this term over to the right, those two terms change sign. So you have F contact by the bucket on the water is mass of the water, v squared over r, minus mass of the water, g. So you want this to be bigger than 0. Bigger than 0 means the bucket is pushing on the water. Smaller than 0 would mean that the bucket has to pull on the water, which it doesn't know how to do. So this is bigger than 0 if v squared over r is bigger than g. So I think that's consistent with my earlier prediction. V squared over r has to be bigger than g at the top of the loop in order for the water to stay in the bucket. And it's the same as keeping the string taut, spinning the tennis ball around fast enough to keep the string taut. How does this thing work? So it seems like we're inside a spaceship. And then it seems like the occupant of this spaceship is jogging. And you can see he looks quite fit, so it does not look as if his muscles have atrophied on this interplanetary voyage. And somehow he's able to run. He's not experiencing zero gravity, but he's running around and around in a circle. And why is he running around and around in a circle? So here he is, he's out in space, and he's in this, basically a centrifuge, which is going around and around at some rotational, some angular velocity omega. And there is no gravity. He's out somewhere between Earth and Mars. By the way, there's a device like this in the more recent movie, The Martian, with Matt Damon. And you can see that they go down a little ladder from the central part of the ship out to the outer radius part of the ship. And it's out in that outer radius part of the ship at the end of the ladder where you find their exercise equipment. So this is worth checking out if you watch. And actually, I want to go back and see The Martian, because I imagine that when they're on the bridge, in the control part of the ship, they're probably seat belted in, because I bet the control part is in the middle rather than at the high radius, but I haven't checked that. So anyway, in this scene from 2001: A Space Odyssey, imagine that the person is up here at this position, which to us looks upside down, but there's really no orientation for what's upside down in space. Then he's accelerating toward the center of that big donut-shaped centrifuge. So his acceleration points down in this picture. So you say, okay, what are the forces acting on him? Well, there is no gravity. He's in interplanetary space. There's no gravity, but there is, I guess there's some gravitational force by the sun, for instance, but basically he's in a zero gravity environment. And the only force exerted on him is the contact force exerted by the floor on the person, which points toward the center. And here, when he's down in this position, let's say, so kind of, what's this? This is like the 7 o'clock position. Then his acceleration is kind of northeast toward the center. So in this case, there's no gravity, but there's a contact force by the floor on the person, which points toward the center. So you see, in order to stay on this surface, he has to keep going around and around in the same circle that the donut is going around in. And that means so if the circle weren't there, if the circle just suddenly disappeared, he would just continue at constant velocity. But in order to bend him into this circle, the floor constantly needs to push him toward the center. Well, that's the same experience as like when the bathroom scale and the elevator has to push you to make you go up with the elevator if the elevator is accelerating upward, or has to push on you even if the elevator is stationary. The elevator has to push on you to offset Earth's gravity. But here we don't have Earth's gravity, The contact force between the floor and his feet is a measure of the pseudogravity that he experiences. The pseudogravity that he experiences actually equals his mass times his acceleration. And remember I told you a couple slides ago in the digression that if he's accelerating this way, then the pseudo force that he experiences is opposite his acceleration. So this fictitious force that he experiences because he's in an accelerating reference frame points upward, points toward the outside of the circle when he's here. It points toward the outside of the circle when he's here. That's the fictitious force. But the actual acceleration points toward the center of the circle and has magnitude omega squared r, or v squared over r. Actually, if you look at it this way, omega squared r, everything in this donut is going around at the same omega, so there would be no fictitious force right at the center. And as you go out farther and farther, the pseudogravity would be bigger and bigger. In fact, this thing has to be big enough that the gravity at his head can't be too much smaller than the gravity at his feet, I think. Otherwise, he'll experience dizziness because the blood pressure balance between his head and his feet won't be quite right. So I think if you were going to design a device like this for interplanetary travel, you would need to make the radius much bigger than a human height so that you do not have a big differential in pseudogravity between the person's head and the person's feet. Because everything is going around at the same omega, but you see the r here is bigger than the r here. Now I have to tell you that we're going to add something new to our picture of kinetic energy. So we've been talking about kinetic energy being 1/2 mv squared for a while now. But now suppose we have an object which is moving around and around and around in a circle. Suppose it's just some tiny little object of mass m. So initially let's just assume it's a particle. A particle is something whose dimensions are so tiny that they don't matter. Or maybe to make things simpler, let's say that this is an object whose size is much, much, much smaller than the radius of this circle it's going around in. Okay? So it's going around and around in a circle of radius r, but somehow the size of this little blob is tiny compared to the radius of the circle it's going around in. Then you say, what is its kinetic energy? Well, we're used to writing kinetic energy is 1/2 mv squared. In this case, we know, since it's going around and around in a circle of radius r at angular velocity omega, that the kinetic energy is 1/2 m times omega r squared, since v is omega r, and this is 1/2 mr squared omega squared. Now, suppose I take my bicycle wheel of mass m. Let's suppose that all of the mass of the bicycle wheel is concentrated on the outside and that the axle and the spokes are of negligible mass. So then the center of mass of the bicycle wheel is not accelerating. In fact, it's not even moving. The center of mass is just staying put right here. And yet, clearly something is happening. In fact, it takes me some effort to start it or to stop it turning around. So there is some kinetic energy associated with this motion because I have to somehow use up some cashy cereal that I've digested to start it spinning. And we'll see later that there is even some variant of momentum associated with this motion. So how do we quantify that? If we have a bicycle wheel of mass m, whose mass is entirely concentrated out here at radius r, except for a negligible portion, which we'll neglect, and the wheel is going around at angular velocity omega. So suppose I divide the mass of the outside, the rim of this bicycle wheel, into a whole bunch of little masses, m1, m2, m3, m4, m5, m6, and then the total mass of the rim of this bicycle wheel is just the sum of all of those individual little masses, so I can sum up over counting up the tiny little masses that compose the big bicycle wheel. So it's as if I built up the bicycle wheel out of a whole bunch of little chunks of bicycle wheel. And I want to work out the kinetic energy of this whole thing. Well, we know kinetic energy, we know energy, and in particular kinetic energy is an extensive quantity. That means if you want the kinetic energy of a system of objects, it just equals the sum of the kinetic energies of the individual object. So I can take 1/2 mv squared, where I take each little mass and each little speed, and I square each little speed, and I multiply it by each little mass, and I multiply by 1/2, and I add everything up. So I need every little mass, and I need every little speed. But we know since this stuff is moving around at angular velocity omega, then each little particle's, each little chunk of mass's speed is omega times r, where r is that little chunk of mass's radius. Now the way I drew this, everything's at the same radius, but it will turn out in a minute that we could have things spread out at different radii if we wanted to, and this expression would still work for the kinetic energy, but everything is going around at the same omega, the same angular velocity. So each little speed is omega times r. So then we can rearrange this expression. So we write the 1/2 out front, and we write the omega squared at the end, because omega is the same for everybody. But then we're adding up all of these little masses times their radius squared. And in this case, all the radius is all at the same place. But again, we'll generalize this in a minute to the case where the radius is not all the same. So we have 1/2 times something times angular velocity squared as the kinetic energy for something whose center of mass is not moving, but whose constituent pieces are all moving around the center of mass at constant angular velocity. So this is called rotational kinetic energy. And let me write a better expression for this. So we have rotational kinetic energy is 1/2 I omega squared, where I is called rotational inertia, and it's the sum over all of the little constituent pieces of an extended rigid body. It's called a rigid body, a solid object which is rotating. The mass of each little chunk times the distance of that little chunk from the axis of rotation. So this quantity down here, the sum of all of the constituents of this rigid body which is rotating around, of the mass of that little constituent piece times the radius, the distance squared of that little piece from the axis of rotation. This is called the rotational inertia. So we had ordinary translational kinetic energy is 1/2 mv squared. This is, m is the mass, which we also call inertia. Mass is inertia. Inertia is mass. So this is 1/2 times the inertia times the square of the speed, and the speed is just the magnitude of the velocity. So this is like 1/2 times mass times speed squared, or equivalently 1/2 times inertia times the square of the velocity. And this is the rotational kinetic energy is 1/2 times the rotational inertia. So this rotational inertia plays the role of m here, times the angular velocity squared. So 1/2 I omega squared. So I is the rotational analog of m, and omega is the rotational analog of v. So this is 1/2 mass velocity squared, and this is 1/2 rotational inertia angular velocity squared. So my bicycle wheel can be simply moving without rotating like this, and it could do that in any direction. Or it can be rotating with its center of mass fixed like this. But normally if I'm riding my bicycle down the street, then the bicycle wheel is rolling without slipping. And in that case, it is both rotating and translating. So its center of mass is, or actually the whole wheel is, the center of mass of the wheel is moving at some velocity. In addition, the constituent pieces of the wheel are rotating about the center of mass at some angular velocity. And we want to write, this is translational motion, so there's a translational kinetic energy associated with that. This is rotational motion, so there's a rotational kinetic energy associated with that. And if I'm riding my bicycle down the street, then there is both translational and rotational kinetic energy associated with the motion of the wheel. And we want to write both parts. For the case where an object is both translating, in other words, its center of mass is moving at some speed v, and it is rotating about its center of mass with angular velocity omega, the kinetic energy has a translational part, 1/2 times the mass of the object times the square of the velocity of the center of mass, plus 1/2 I omega squared. This is 1/2 times the rotational inertia times the square of the angular velocity of its rotation about its center of mass. To calculate this rotational inertia, we adding up over all of the little constituents that we imagine this object is made out of. We take the tiny little mass of each constituent times the distance of each constituent from the axis of rotation, And for the moment, we're assuming the axis of rotation coincides with the center of mass. And you can make that a sum if it's a discrete set of objects, or if it's a continuous object, like a hula hoop or a baseball or a wheel rolling down the street, then you can make this an integral instead. And you integrate over little differentials dm, the radius squared, the distance squared from the axis of rotation. You won't have to work out this integral in this course. You might be able to if you want to for extra credit. Instead, for common shapes of objects, the rotational inertia is tabulated, and so you can just look it up. So we will see tabulated in tables values of the rotational inertia for various shapes. For example, a hoop like this bicycle wheel with all of its mass concentrated at radius r has rotational inertia mr squared. A solid disk, so if you took this and instead filled it in so that the mass is spread uniformly throughout the circle, then the rotational inertia would turn out to be 1/2 mr squared. If you have a hollow sphere, so something spherical, but all the mass is at the outside, that turns out to be 2/3 mr squared. Or if you have a solid sphere, so a spherical ball whose mass is uniformly distributed inside, that turns out to be 2/5 mr squared. And if you have a long, thin, solid rod, like a long, thin ruler, about its center of mass, that turns out to be 1/12 ml squared, where L is the length from end to end. You don't have to remember any of these. It's sometimes useful to remember that they all look like mass times the square of the size, and then there's some factor, and you have to figure out which size to use. But in general, you just look this up in a table. An ice cube and a rubber ball are both placed at one end of a warm cookie sheet, and the sheet is then tipped up. The ice cube slides down with virtually no friction. This turns out to be unrealistic, but let's suspend our disbelief. And the ball rolls down without slipping. Which one makes it to the bottom first? They reach the bottom at the same time. The ball gets there slightly faster because the ice cube's friction, while very small, is kinetic and dissipates some energy, while the rolling ball's friction is static and does not dissipate energy. Well, we said the friction was virtually negligible. The ice cube gets there substantially faster because the ball's initial potential energy, mgh, gets shared between 1/2 mv squared translational and 1/2 I omega squared rotational, while essentially all of the ice cube's initial mgh goes into 1/2 mv squared translational. Oh, gee, I think I like that. The ice cube gets there faster because the ice cube's friction is negligible, while the frictional force between the ball and the cookie sheet dissipates the ball's kinetic energy into heat. Well, we know that the frictional force between the ball and the cookie sheet is the kind that creates rolling without slipping, and that is static. So we know that the frictional force between the ball and the cookie sheet does not dissipate any energy because static friction does not dissipate energy into heat, whereas kinetic friction does dissipate energy into heat. So I think we can rule out D. And for B, I think we can use the argument that we were told that the kinetic friction was virtually negligible. So I think that kind of rules out B. Otherwise, it might be promising if the kinetic friction were big. And, well, I think argument C would tend to contradict A as long as... So let's see if we can work through C and see if argument C makes sense. So the ice cube just translates down the ramp. It just slides down the ramp. It's not rotating, it's just sliding straight down the ramp. Whereas the ball is rolling without slipping as it goes down the ramp. So for the ball, there is both translational kinetic energy and rotational kinetic energy. And as a matter of fact, the rate of rotation is related to the speed downhill, because if the ball rolls without slipping, then every time the ball goes around 2 pi radians, it must move 2 pi r distance. So every time the ball moves a distance 2 pi r, it must go around 2 pi radian. So rolling without slipping turns out to have the speed related to the angular velocity by the expression v equals omega r. For the ice cube with only translational kinetic energy and negligible friction, the initial gravitational potential energy turns into the final kinetic energy. Initially, the energy all takes the form of gravitational potential energy, mgh, and in the final state, we're down at h equals 0, so all of the energy is in the form of kinetic energy, which is 1/2 mv squared. So we'll call this v final, 1/2 mv final squared. For the ball, you have both translational and rotational kinetic energy. And the friction that we have is static friction. Static friction does not dissipate kinetic energy into heat. And we know that the ball rolls without slipping. And rolls without slipping means v equals omega r. Maybe we'll make a better argument for that in a second. So we say the initial gravitational potential energy gets turned into the final kinetic energy. So here we have mgh at the beginning, but the kinetic energy has two terms, 1/2 mv squared plus 1/2 I omega squared. So since these two things together have to add up to this is the same, let's say they're the same mass. So it's the same mgh, but now since these two terms together have to add up to this term must be smaller than this term. So the final speed must be smaller than the final speed of the ice cube. The two speeds start out 0. The final speed of the ice cube is bigger than the final speed of the ball. And in fact, you could make the same argument for any intermediate point. And at any intermediate point along the path, the speed of the ice cube will be faster than the speed of the ball by this same argument, because you could just pretend the hill is half as high or a quarter as high or an eighth as high. So as it rolls down. So since at every instant along the way, once they start moving, the ice cube is going faster than the ball, the ice cube must reach the bottom sooner. So for translational motion only, with no friction or negligible friction, we can just solve this for v final, and we get v final as the square root of 2gh. What happens for the ball, which rolls without slipping? Let's see if we can use this relationship and figure out something similar. So it seems like for the object that rolls without slipping, once we use this relationship that omega equals v over r if the object rolls without slipping, then we get very similar math. We have this 1/2 mv final squared plus 1/2 I omega final squared, but omega is just v over r for rolling without slipping. Then we can divide both sides by m, and we can multiply both sides by 2 to get rid of the 1/2. And see, this is the same thing we had over here. 2gh is v final squared, but we have this extra term, but the extra term has a v final squared in it, so we can factor that out. So we have this v final squared, and then there's this 1 plus I over mr squared. So then, if we solve for v final, we get v final is the square root of this whole thing. The whole thing is 2gh upstairs and 1 plus I over mr squared downstairs. So apparently v final is indeed smaller in this case than it is in this case. And it's smaller by, see the factor, the square root of this denominator. And this denominator for like the bicycle hoop would be 2, because I equals mr squared for the bicycle hoop. V final for the bicycle wheel would be smaller than v final for just simply translating without rolling by a factor of 1 over square root of 2. And for different shapes, that factor would be different. So we said, for like a ball, actually it turns out that I is either 2/3 or 2/5 mr squared, depending on whether it's a hollow ball or a solid ball. So we don't need to know the exact details. We know that v final will be smaller for the ball than it will be for the ice cube, assuming that the ice cube slides without any kinetic friction. And by a kind of tricky argument, which maybe we can clean up later, not only is v final smaller, but every intermediate speed is also smaller for the ball than for the ice cube. Therefore, the ball must take a longer time to get down than the ice cube. Well, having the tiny little wheels underneath this matchbox car will create the effect that there's virtually no friction. So this thing will go down. So when this matchbox car rolls down the hill, we'll get essentially the same motion that we would get for something sliding down the hill without any friction whatsoever. Okay, then the other case is a rubber ball. If you watch the little marbled pattern on it, I think you can see. So it's not doing that, it's doing that. You see, this is called rolling without slipping. In fact, you can see it more clearly here. It's not doing this, it's doing this, which means that every time it goes downhill by one circumference, It's rotating around its own center one time. We have a rubber ball. We don't have an ice cube, but this is going to be our ice cube. Now, will they reach the bottom at the same time, or will one of them reach the bottom sooner? The little matchbox car slides down the hill. Now, suppose we do that for the rubber ball. Let's see what happens. A hollow cylinder and a solid cylinder both roll down an inclined plane without slipping. Does friction play an important role in the cylinder's motion? Well, I guess you can imagine, suppose you're riding your bicycle, and you imagine you're trying to ride your bicycle down a sheer sheet of ice. Do the wheels turn, or does the bicycle just slip? So you say, friction plays a negligible role. Yes, kinetic friction dissipates a substantial amount of energy as the objects roll without slipping down the ramp. I don't think I like either of those. Yes, static friction is what causes the objects to roll rather than to slide. Without static friction, they would just slide down, so there would be no rotational motion. If you just let go of each cylinder from rest at the top of the ramp, then there's nothing that starts them rotating. Let's see if we can see that with the bicycle wheel. So if I let this bicycle wheel go down a sheer sheet of ice, there's nothing that starts the wheel rolling. The bicycle can just slide, can just translate down the hill. It's friction which causes the bicycle wheel to roll without slipping as it goes down the hill, because every time the wheel goes forward by 2 pi r meters, it has to go around by 2 pi radians. So every time the wheel makes a complete revolution, 2 pi radians, the center of the wheel has moved by 2 pi r in distance. Why are people who write physics problems, for example about cylinders rolling down inclined planes, so fond of the phrase rolls without slipping? Maybe nature abhors the frictional dissipation of energy. Maybe rolls without slipping implies that v equals omega r, where v is the cylinder's translational speed down the ramp. This lets you directly relate the rotational and translational parts of the motion. And when you can do that, you have a good physics problem. No good reason you could analyze the problem just as easily if the cylinders were slipping somewhat while they roll. Actually, it does really make things much simpler. It makes for a much better physics problem if an object rolls without slipping, because then there's only one variable, the same variable that quantifies how far it moves. Translationally, can also be used to quantify how far it rotates rotationally. And one way to see that is if you notice if this object rotates without slipping. I mean, if it slips, then there's no connection. But if it's really rolling without slipping, so there's no screeching sound, there's no sliding, it's like this is like your bicycle wheel when you're not skidding, then if the wheel makes one complete revolution about the center, which is 2 pi radians, then the distance that it moves forward is one circumference, which is 2 pi r. So the angle as a fraction of 2 pi, in other words, the angle as a fraction of a revolution, is the distance as a fraction of the circumference. The angle in rotations is the distance in circumferences, so theta over 2 pi is the distance over 2 pi r, so the distance is r times theta. That's that familiar result from before where we said the arc length is r times theta if you measure theta in radian. Well, the rate of change of distance is the speed, and the rate of change of theta is the angular velocity omega, so we get speed is the radius times omega. We usually write it the other way. Speed is omega r. So we have speed is omega times r for an object that rolls without slipping. And that makes a good physics problem. That means that we can relate the rotation rate to the translation rate. Not only does it make a good physics problem, but it describes a lot of everyday real life, like the wheels on your car rolling down the street, except when you're slipping on sand or you're jamming on the brakes and screeching. How do I write the total kinetic energy of an object that has both translational motion at speed v and rotational motion at speed omega? Well, I think we want to say that the kinetic energy has a translational part, 1/2 mv squared, and it has a rotational part, 1/2 I omega squared. And this is mass, which we also call inertia. This is rotational inertia. This is velocity. It's squared. This is angular velocity squared. One thing that's tricky about this is mass, or inertia, is measured in kilograms. Rotational inertia is measured in kilogram meters squared, because you know rotational inertia always looks like mass times the square of radius times some factor. And velocity is measured in meters per second. Angular velocity is measured in radians per second, which is the same as just per second. So because a radian is a dimensionless unit, this omega squared, it's radians per second, the quantity squared, but when you write out the units, it's just per second squared. Let's see which one of these answers seems right. I don't like that. I don't like that. I don't like that. I think I like that. Yeah, and then these are just misspellings on purpose. So I think I like D, delta here. I left this result that we worked out earlier here because now we finally are working through it once again on slide 23. For translational motion with no friction, V final is square root of 2gh because you just take the initial mgh, and it all gets converted into the final 1/2 mv squared. If you want to roll without slipping, then you have v equals omega r, which gives you omega is v over r. So then we can do the math we did earlier, letting the original mgh turn into the final 1/2 mv squared plus 1/2 I omega squared. But we can now plug in omega equals v over r, and we get this V final. Instead of V final equals root 2gh, we get V final is root 2gh divided by 1 plus I over mr squared. This is called the shape factor, this I over mr squared, or I think maybe it's sometimes this whole 1 plus I over mr squared is called the shape factor, because it depends on whether it's a solid cylinder or a hoop or a solid sphere or a hollow sphere or so on. A hollow cylinder and a solid cylinder both roll down an inclined plane without slipping. Assuming that the two cylinders have the same mass and the same outer radius, which one has the larger rotational inertia? Well, maybe the hollow cylinder has the larger rotational inertia because the material is concentrated at a larger radius. That sounds plausible to me. Maybe the solid cylinder has the larger rotational inertia because the material is distributed over more area. Well, I think if some of the mass is in here at low radius, then there's less of it available to be out at high radius. The rotational inertias are the same because the masses and the radii are the same. Well, this expression for the rotational inertia, so you divide up the mass into a whole bunch of little chunks, and for each chunk, you take that little chunk of mass times how far it is squared from the axis of rotation, or from the center of mass. And here, all of the mass is out here at r. Here, a tiny bit of the mass is out here at r, but really the bulk of it is kind of in between, at some intermediate value of r. So I think in this case, the mass is on average closer to the middle, whereas in this case, the mass is all at the outside, big R. So I think if we were going to do this big complicated sum, or this integral, we would get a smaller answer here because the mass is on average closer to the axis. Whereas here, the mass is all way out at R. You see the farthest mass here is at R, but it's only a little bit of it. Most of it is closer than R. Here, all of it is out at R. So I think we have a bigger rotational inertia for the hollow cylinder, a smaller rotational inertia for the solid cylinder. Meanwhile, I think that an object with a bigger rotational inertia will be going at a lower speed when it reaches the end, because if the mass is the same and the radius is the same, but you make this rotational inertia bigger, then you're making this denominator bigger. And if you make this denominator bigger, then you make the final speed slower. And if you make the final speed slower, I say you get to the end of the ramp later. So I think if you have a race between this object and this object, both rolling without slipping down a ramp, I think this solid object will get to the bottom sooner. I think the hollow object will take longer to get to the bottom because this I, this rotational inertia factor, which is living downstairs here, part of the denominator, it's kind of like an upstairs part of the denominator downstairs, it is going to be a bigger factor. for the hollow cylinder than for the solid cylinders. I think the hollow cylinder will reach the bottom later than the solid cylinder. Here's a solid cylinder, and here is a hollow cylinder. When these objects roll down, they're not going to slide like this, which is what would happen if there were no friction. They're going to roll without slipping. So this is rolling without slipping. So when we do rolling without slipping, every time the object moves downhill a distance of one circumference, it also rotates one full revolution cylinder. So it turns out that for a hollow cylinder, I equals mr squared. And so this whole factor inside the square root is 1/2. So it's like square root of 1/2. For a hollow sphere, I equals 2/3 mr squared. And so it works out that the factor inside the square root is 0.6. So it's square root of 0.6. It turns out for a solid cylinder, like this one, I equals 1/2 mr squared. That means that this square root, the factor inside the square root is 2/3. So that's square root of 2/3. And then it turns out for the solid sphere that I equals 2/5 mr squared. And then when you do all the math, it turns out that the factor inside the square root is 0.71, so it's the square root of 0.71. So if we have a race downhill, rolling without slipping between these various objects, then we expect the hollow cylinder to be the slowest, and we expect the solid sphere to be faster. We expect the solid cylinder to be just a tiny bit slower than the solid sphere. And we expect the hollow sphere to be just a little bit slower than the solid cylinder. So we expect the hollow cylinder to be slowest. And this factor is 1 for something that just translates. It just goes right down the hill without any friction and without rolling. It's just translating. Now it turns out that one way to get something to go down the hill as if it had no friction. Imagine what you do if you want to roll a heavy box across suppose you want to move a big heavy box across the floor and you want to pretend it has no friction. Well, you could put it on an ice rink, but sometimes that's inconvenient. You don't have an ice rink available. So instead, you can put it on really good wheels. And if you put it on little tiny wheels, and the wheels are so small, the mass and the size of the wheels are so small that the rotational inertia of the wheels themselves is negligible, then you get motion that looks like purely translational motion without a rotational part. That only works if you arrange so that the mass of the object itself is big and the masses and the sizes of the little wheels are tiny in comparison. And if the friction of the wheels is tiny, it means the wheels have like good wheel bearings or they're well lubricated. So we can take like a little matchbox car, a little toy car, and it will play the role of the ice cube. And then we think it will always win. So the little toy car will always win because all of its motion, except for a tiny little fraction, is translational. And then the one that will always lose is the hollow cylinder. And then we'll see that these other objects, the hollow sphere, the solid cylinder, the solid sphere, are somewhere in between when we see that demo. Let's try something even a little more extreme. Let's replace the ball with a hollow cylinder. So I think you'll see a very dramatic difference here. Let's see what happens. Okay. Okay. So if you have an extended object composed of several particles with different particles having mass mj and distance rj from the rotation axis, so we're kind of summing over some little summation variable j that enumerates all of the particles, all of the teeny little constituents that make up this extended object. And this extended object is often called a rigid body because the constituents of this extended object stay rigidly attached to one another. Then we can add up over all of the little constituents the mass times the distance squared from the rotation axis of all of these little constituents. If you have a continuous object like a sphere or a solid cylinder, then you have to integrate instead of adding, but more commonly you just look up the answer in a table. So these answers are tabulated. So it's the integral of r squared dm. But we might, except for extra credit, we will not calculate these ourselves. We will just look them up. So if you arrange that same total mass and you put it at a larger distance from the axis of rotation, you get a larger rotational inertia. So in the next clip, I'm going to show you an object which consists of, there's a lightweight wooden hoop, and the wooden hoop has a pretty small mass. And then there's this metal rod, which is also pretty lightweight. And then there are these two big masses, which are actually, they dominate the mass of this object. And I can adjust their position. I can put them far out toward the outer radius, or I can put them close to the axle, close to the center. And it's the same total mass, but in one case the mass is close to the middle, in the other case the mass is far outside. Which one should have the larger rotational inertia? So it's the same total mass, but here the mass is far out, here the mass is pretty close. So I think the rotational inertia should be much bigger for this case. It should be smaller for this case. And then you say, if I have a race where I roll them both downhill, which one will win if they're both rolling without slipping? Well, if they're both rolling without slipping, I think this one will win because this one has to put more of its energy into the rotational kind. This one can have a smaller fraction of its energy in the rotational kind. More of it can go into the translational term. And then more mathematically, that downstairs factor 1 plus I over mr squared, well, this has a bigger I, this has a smaller I. So I think this one will take a longer time to get down the hill. This one will have a smaller final velocity. This one will have a bigger final velocity. It will take less time to get down the hill. So let's watch the race. In this case, the material is closer to the center. In this case, the material is more spread out. So I think this guy will win every time. Let's see. Yeah. I have a slide here summarizing the new terms we've been learning. So we have inertia or mass, m, whose rotational analog is rotational inertia, I, where I is determined by taking all of the constituents of a rigid body, or what our book calls an extended object, and for all of those constituents, you add up the mass times the square of the distance from the axis of rotation. And in our case, usually the axis of rotation is the center of mass. Then we have translational velocity, v, and the angular equivalent of that is the angular velocity, omega. So this mass, or inertia, was kilograms. This rotational inertia is kilogram meters squared. Kilogram meters squared. This translational velocity is meters per second. This angular velocity is radians per second, which is also known as per second, because a radian is a dimensionless unit. Angular velocity is also sometimes called rotational velocity. So angular velocity and rotational velocity are two terms for the same thing, omega. We have translational kinetic energy, 1/2 mv squared. The rotational equivalent is rotational kinetic energy, 1/2 I omega squared. This is 1/2 inertia velocity squared. 1/2 rotational inertia angular velocity squared. There's also an analog to momentum. We had P equals mv. We're going to see next time, we're not going to do it yet, next time we'll see that there's angular momentum, L equals I omega. So this is mass times velocity, or inertia times velocity. This will be rotational inertia times angular velocity, but we've given you enough to digest for now. So we'll do this next time in the next video. So we'll spend next class working with these new ideas.